Welcome back, everybody, to our course on memory device technology for AI/ML computing. I'm your instructor, Dr. Shubhadeep. Before we begin today's class, let's do a brief recap of the new module that we started in the previous class. So basically, in the last class, we saw how modern CPUs and GPUs were incredibly powerful. However, when compared to the brain, their energy efficiency was orders of magnitude lower. And that led us to ask, how can we bridge this gap? On one side, we had biological computing, the brain, with its massive parallelism, adaptive nature, and remarkable low power feature. But on the other hand, we have AI/ML algorithms, which can nowadays even match or surpass human performance, but it requires large number of computational and energy resources. The real limitation, as we discussed, was in the hardware implementation. That's where neuromorphic computing comes in, combining the brain-inspired principle with circuit and device-level innovations to achieve energy-efficient intelligence in CMOS-compatible hardware. We compared von Neumann computing, where computation and memory are separate and clock-driven, with a deep learning, which uses parallel dense computation but still inherits the von Neumann bottleneck. And therefore, we move towards neuromorphic architectures, which are essentially event-driven, locally connected, and have massive parallelism. And this is how you are able to, in principle, mimic how the brain processes spikes rather than continuous signals. We also saw some examples like the event-driven camera, which record only when changes occur, drastically reducing redundant computation. Historically, we trace this evolution from Turing's intelligent machinery coming out in 1948, the Hebb's learning rules, to Carver-Mead's silicon retina in the 1980s. We also looked at the recent demonstrations from companies like IBM in form of TrueNorth and also Intel's Loihi project. We also saw that the next trends will be in emerging device technologies such as eNVMs, where you will move from neuromorphic devices, or rather you will embed neuromorphic devices inside neuromorphic computing. And this leads us to the main question: how can we actually build such brain-like systems using existing CMOS compatible semiconductor technology? Can our memory devices and transistors that we have been studying throughout in this course start acting like artificial electronic neurons and synapses? So to begin today's class, what we will do is we will look at the signal transmission that happens in neurons and synapses in the biological brain, and also we will ask the question, can we create an artificial electronic neuron, before we move on to looking at the behavior of synapses. But before that, I would like you to develop the habit of reading some review papers. So I have presented 3 papers for you. Paper 1 and paper 2 are essentially only available through an academic institution. So you can either get it from your own institute or you can contact some of your friends. However, paper 3 I have kept as completely open access. If you have an internet connection, which you of course have because you're watching these lectures, you will be able to access the third paper very easily. So the idea is very simple. Reading papers is very essential for the development of scientific knowledge, especially in fields which are evolving so quickly, such as neuromorphic devices and also memory devices. So my suggestion is go through 1 or 2 of these papers in detail, especially the introduction part, and the subsequent portions you will be able to appreciate as we go ahead in our course. Okay, so with this note, let us begin with what we wanted to discuss today. We wanted to see how signal transmission happens from the perspective of neurobiology and then move to electronic devices. Now, a fair bit of warning. We are not going to study all details of neurobiology because neurobiology is an extremely vast field. But for our purposes, what we will do is we will focus on the aspects that are only essential for understanding how biological computing can inspire hardware design. So we will not go into the nitty-gritty biochemical or biophysical details. We will only look at certain aspects. And to help you out, I have tried to remove all the clutter and circled the parts which we need to know for our course. But nonetheless, let's have a very quick understanding of some of these details. So if you look at the basic structure of the neuron, the first thing that pops out is these dendrites. So what do the dendrites do? They act like input terminals. They receive the electrical or chemical signals from many other neurons. And as we will see, one neuron is generally connected to 10,000 other neurons. So there are many such dendrites which are simply collecting this information in electrical and chemical signals. So where are these signals collected? They are collected in the so-called soma, or the cell body of the neuron, which integrates all the incoming information. You can think as the soma or the cell body as the neuron's processing unit, where it sums up all the signals and also decides whether this particular neuron, which we have circled, will fire or will it remain silent. So once that decision is made, and we will see how that decision is made very, very soon, the signal is sent down by this long cable, which is known as the axon. This is like a large transmission line. The first segment of this transmission line, which is very closest to the soma, is also called the axon hillock. This is where the action potential or the spike is generated from this particular neuron cell. The axon is often covered by something called the myelin sheath, which you see here in this yellow covering. And this helps the signal travel faster and with much less energy loss. At the end of the axon is another interesting thing. For our purpose, we reach the presynaptic terminal, which communicates with the postsynaptic dendrites of another neuron through the small gap which is known as the synaptic cleft. Remember, there will be lot of such. This neuron itself will be connected to many other neurons. And these terms, which we will see very soon, is the presynaptic neuron, which is sending the pulse, and the postsynaptic neuron, which is receiving the pulse. How does it receive the pulse? Again, through its own dendrites. As you see, the dendrites of the postsynaptic neuron is connected to the presynaptic terminal through the most important functional element, which is called the synapses. Now, how these synapses work, we will discuss a couple of classes later. Okay, so now that we have seen the structure of neurons and synapses, let's talk about how they actually communicate and why that is such a huge challenge to reproduce in hardware. So as I have indicated in this slide, neurons communicate with each other using action potentials, which are these small electrical spikes that travel through this axon. But what is really remarkable is that this communication is both electrical and chemical. We will discuss some details in this and subsequent classes. Inside the neuron, the signal travels electrically, but when it reaches the synapse, it becomes chemical, and neurotransmitters are released to activate the next neuron or to transfer that information to the next neuron. Now, very important to realize is the total number of neurons that we are dealing with. So a common human cerebral cortex consists of almost 10 to the power of 11 neurons, which is around 100 billion neurons. Now, each neuron, as I discussed, is connected to 10 to the power of 3 other neighboring neurons, or sometimes even 10 to the power of 4 other neurons. And as we discussed, the junction between the pre and post synaptic neuron is the so-called important element called synapses. And this massive connectivity of 1,000 to 10,000 with other neurons forms this enormous web of interconnections. And this massive connectivity is what makes it incredibly difficult to mimic in hardware. Why? Because this high fan out is very, very difficult to reproduce in hardware systems. See, in CMOS circuits, to get a fan out of even 10 or 100 becomes extremely difficult until you start introducing other elements such as buffer circuits or strengthening the signal. And it's not that people have not tried to mimic the entire functionality of the brain. The IBM Blue Brain project actually managed to simulate just 1% of the human brain using CMOS compatible hardware. But while the actual brain, 100% of it, works on about 20 watts, your IBM Blue, to mimic just 1% of the brain, required several megawatts of energy. And that's an astonishing difference. And that is why in neuromorphic computing, you do not try to copy each and every aspect of biological computing. Instead, you focus only on mimicking the essential elements like spikes and synapses and local learning, which makes a brain such a powerful and energy efficient computing system. With this understanding, let's move on and simplify the earlier picture that we had. On the left hand side, as you can see, we have this presynaptic neuron which is sending the action potential, and on the right you have the postsynaptic neuron which is receiving the action potential. So when the presynaptic neuron gets activated, it generates this action potential, and that is what travels through this axon, and it's always in one direction. So here I have shown you a voltage versus time characteristics of one of such action potentials. So at the synapse, the signal is transmitted to the next neuron, but this junction does more than just pass the signal. It actually controls the strength of the connection between the two neurons, and you can relate it back to your artificial neural networks, where the synaptic weight was controlling how much of the input signal was controlling the multiply and accumulate product. And this adaptive tuning of synaptic strength is what we will finally aim to reproduce in neuromorphic computing systems. So here is a very nice GIF which shows the signaling of the action potential. Let me play that again for you. So as you can see, the action potential is going down the axon, going to the dendrites and releasing the neurotransmitters into the synaptic cleft. So I would really like to thank Professor K.C. Henley from Michigan State University for creating this very nice GIF and a couple of other GIFs which I will use in my subsequent slides. Therefore, to summarize, the signal transmission, signal flows only in one direction from the pre to the postsynaptic neuron, and these synapses basically modulate the strength of these connections, and this tunable strength is what brings in the learning and the adaptation which is commonly seen in biological computing. Good. Now that we understand the signal transmission, let us go ahead and focus on the structure of a single neuron. Remember, we are only going to look at elements which are absolutely essential for mimicking computation using artificial hardware. So, as we have already discussed, the neuron that we have singled out over here is connected to thousands of other neurons through these dendrites. The next important thing that we will look at is the sheath which covers the neuron's soma or cell body. So the neuron is wrapped in a neuronal sheath which is a bilayer phospholipid membrane. And this bilayer phospholipid membrane is the most important functional element of this entire neuron. Why is this the case? Because this is not simply a passive covering membrane. It has voltage controlled selective permeable gates or channels to pass through ions like sodium, potassium and chlorine. And these ions which surround the neuron both inside and outside, and their movement through the membrane is what generates these action potentials or electrical signals. Again, let me show you this wonderful GIF image which is created by Professor K.C. Henley from Michigan State University. Let me play it once again for you. You will see that through these selective ion gated channels and voltage controlled channels, you are allowing certain ions to pass through, in this case sodium ions, while you are blocking off other ions. And as you might anticipate, the separation of these ions is what creates this potential gradient or the electrical gradient. So at rest potential, the neuron maintains a membrane potential of roughly minus 70 millivolts, meaning the inside of the cell is actually negatively charged compared to the outside of the cell. And this is evident when you see this image where the number of positive ions outside the cell, so this is the outside portion of the cell, is more than that in the inside of the cell. So the net potential difference at rest, which is also called the membrane potential, is roughly minus 70 millivolts. And as we have seen in the previous animation, this is maintained by ion pumps and voltage gated channels, which are embedded in the membrane, which either open or close depending on the changes in voltage. And as you have seen in the animation, that when you allow selectively the positive ions to enter inside the cell's body, you change this potential. You make the potential from slightly minus 70 millivolts to slightly more positive, because now there is a more balance between the positive ions inside and outside the cell. So now what happens is, when an incoming signal arrives from other neurons, what they can do is they can either increase this membrane potential, making the neuron more likely to fire, and that is called the excitatory input, or decrease it by making it less likely to fire, and that is called inhibitory. How this happens depends on the behavior of synapses, which we will discuss a little later on. So basically the point that we are trying to make is that neurons are this very complex electrochemical systems where electrically charged, voltage controlled, and dynamically interacting with the surrounding medium based on the ion flow across their membrane. So how do we understand the neurons' electrical behavior? So way back in 1950s and 60s, people made these very intelligent setups which were called the clamp voltage measurements, which allowed you to inject certain pulses inside the neuron, which has been isolated in vitro, means inside a solution, and measure what happens to the membrane potential. And this is what is indicated in this setup. This is a voltage clamp experiment, which is a classical electrophysical technique used to study how these biological neurons respond to current inputs. What you do essentially is you keep this particular neuron, which I have marked out with orange color, alive in a saline solution which mimics the ionic environment of the brain, using two micro electrodes that you see here in black color. Using the first one, what you do is you inject a controlled input current into the neuron, while the other one continuously measures the membrane potential as a function of time. The measured voltage is then displayed on an oscilloscope after being passed through certain denoising and filtering, and we can observe how the membrane potential changes. And that is what helps us to understand what is the electrical behavior of the neurons. And it turns out, although the biophysical mechanisms which involve in this electrical behavior can be very complex, as we have seen in the previous slide, the actual electrical behavior which we care about as electrical engineers, why? Because we want to mimic it, is rather simple. So let us look at the electrical behavior of these neurons. So as we have been discussing for quite some time now, these action potentials arrive for neighboring neurons, which can be of two natures. They can either be inhibitory or they can be excitatory in nature. So how does the inhibitory or excitatory influence the neuron's electrical behavior? It does that by changing the membrane potential. Remember, the membrane potential was the potential that is maintained within the neuron's cell body and the outside environment. So as you can see, the first input that is received was inhibitory in nature, and when this was received as indicated from this blue arrow, it reduced the membrane potential, whereas the second input that was received was excitatory in nature, and therefore it has increased the membrane potential. Let's see what happens when a bunch of excitatory impulses reach this particular neuron. So as you can see, what will happen in this neuron is there will be an integration of these incoming signal. As you can see, excitatory increases the membrane potential, the inhibitory reduces the membrane potential. But it is important to understand that this integration is not a perfect integration. It is an integration with a leak, as is very nicely illustrated in this particular graph, which plots the membrane potential as a function of time. When the excitatory impulse arrives, of course, there is an increase in the membrane potential, but also there is this leak or decay. You see, there is a leak or decay until the next one arrives. Like all biological systems, the increase in the membrane potential does not want to stay in this excited state. It wants to go back to its rest state. And that will keep happening until there is another excitatory action potential which arrives over here. And after a couple of more such excitatory impulses, remember the magnitude and the direction of whether it is excitatory or inhibitory and how it changes the membrane potential is all determined by the synaptic weights which are at the junction of these dendrites and the previous neuron's axon. And as we were discussing, after a couple of these leaky integrations, it so happens that the membrane potential reaches the threshold membrane potential. Remember, there are two kinds of membrane potential. One is your rest membrane potential, another is your threshold membrane potential. When it reaches its threshold membrane potential, this is typically around 55 millivolts. The neuron gets a signal that now it should fire. So this firing is essentially an action potential, as you can see, which travels through the axon. But once this firing event is over, what happens essentially is the membrane potential quickly returns back to the resting level of around minus 70 millivolts, ready to be used for the next cycle of computation. So to sum up what we have seen, in essence, neurons act like integrator and threshold detectors. They sum up incoming inputs and fire only when the combined signal is strong enough to cross a particular threshold. And what is really fascinating is that this very simple mechanism enables very complex behavior. What are these complex behavior? A single neuron can filter out noise, since weak random inputs decay very quickly before it reaches threshold. Only the strong synaptic weights makes a single neuron fire. The first thing. The second thing is the timing of the spikes can now start encoding information, not just the presence of activity, but when it occurs. And this temporal encoding of information is what makes brain-like computing very robust and very low power. And this is what we will try to mimic in the last portion of our course. Finally, the interplay of excitatory and inhibitory neurons create incredibly rich dynamic system. And this is what gives biological brains their efficiency and adaptability. So this summary of information is a leaky integrate, not perfect integration, but with a tendency to leak back to its rest potential. And once this threshold is met, the neuron fires. So a natural question then which comes to our mind is, how do we implement this leaky integrate and fire model using CMOS compatible hardware, using basic electronic components? So let me give you a hint. Let's start with the leaky integrate part. In your study of basic electronics, have you seen any component which does an integration, but it does it in a leaky fashion. You might have guessed, yes, you have seen such elements. That is your RC circuit. Remember, when you have an R and C in parallel, whereas the capacitor integrates the charge which is arriving from input current impulses, the resistor leaks out the stored charge in the capacitor when these impulses are not present. And this is what is indicated by this very simple leaky integrate RC model. So as you can see in this model, there is this injected current which is arriving from neighboring neurons, and when a current impulse arrives, it ends up charging this capacitor. It has a charge of Q. But in the absence of any injected current, this charge which was stored in the capacitor is also being able to leak out through this parallel resistor. Therefore, the resistor represents the leaky nature of this neuron. It slowly discharges the capacitor, preventing the voltage from increasing indefinitely. And this interplay between charging and discharging gives you the characteristic leaky integrate behavior. One thing that I would like to indicate is this battery with a rest potential of Vrest. Remember, in biological systems also, this rest potential is generally not zero. So when no activity is happening, this membrane potential, which is at the parallel connection of this leaky resistor and storing capacitor, is this membrane potential. So this simple circuit mimics the leaky integrate part of your neuron. Now, what about the firing part? For including the firing part, that is the role of your voltage comparator. So when the membrane potential over here reaches the threshold voltage, the comparator triggers with an output spike, and immediately afterward a feedback mechanism, as you can see over here, resets the capacitor to its resting potential, therefore completing the fire and reset cycle. So effectively, this entire simple circuit captures the complexities of neuronal dynamics. The capacitor integrates, the resistor leaks, and the comparator just simply fires and resets. It's very elegant and it is completely CMOS compatible. We can build it out of transistors, resistors, and capacitors which are available in semiconductor fabrication process. And that is why this kind of leaky integrate fire neuron, which is CMOS compatible, has been used in prototype neuromorphic chips. However, there is a major challenge. While this approach is conceptually sound, it is not very scalable. To implement these, even a modest sized neural network, we will need thousands or millions of these RC comparator circuits. Since each neuron consumes a considerable amount of chip area and power, especially because capacitors are very bulky. We saw that when we were studying DRAM. And comparators require continuous biasing and several transistors. This particular design is not scalable. And this is what brings us to the next step in neuromorphic hardware. The solution is to build devices, a single device that can inherently emulate the integrate and fire behavior within a single nanoscale element. And that is the field of neuromorphic devices. By using different kinds of memory and switching elements that naturally mimic the function of neurons at a fraction of the area and power that is needed by these bulky circuits, we will be able to realize the potential of brain-inspired hardware. And that is what we will go on to discuss in the next class. But before that, let me leave you out with a homework problem. Can you write down all the equations which are involved in this circuit to represent the membrane potential? Please try this on your own. We will anyways do it in the next class. Thank you for your attention. See you in the next class.